Let us look at proposition number 23 of works of Archimedes, specifically from on conoids and spheroids. The proposition says if from a paraboloid of revolution, two segments be cut off, one by a plane perpendicular to the axis and the other by a plane not perpendicular to the axis. And if the axes of the segments are equal, the segments will be equal in volume. So let's prove this step by step. So we are given a paraboloid. Let two planes cut off segments of the paraboloid, one by a plane perpendicular to the axis and the other by a plane not perpendicular to the axis. So this is one of the planes which cuts the paraboloid not perpendicular to the axis. And the other one is this. This is perpendicular to the axis of the paraboloid. Okay. Now, each of these actually intersect the paraboloid in a conic. Yes, this is one and this is the other one, right? Now let a plane through the axis cut the above planes at right angles in BB prime and QQ prime and cut the paraboloid itself in the parabola QPQ prime B prime. So let's do that. This is the plane through the axis cutting the other two planes, right, in BB prime. So to get the BB prime and QQ prime, let's take the intersection of the paraboloid with this plane. So now the intersection of this conic with the intersection of the other two planes with the paraboloid, let's take the intersections. So the intersections would be B prime. You notice here it is the intersection of this plane and this plane. So let's join BB prime. And similarly, Q prime. You will notice that this is the intersection of this plane and this green plane. And let's join these two lines, these 2 points. And let's take the axis AN and PV, axis of the segments of the parabola. So let's take AN and PV. This is A and N. And this is PV. This is P and this is V. The construction has been done in such a way that AN is equal to PV. That means the axes of these two segments of the paraboloid are equal. And A and P are their respective vertices. Now draw QL parallel to PV or AN. QL is parallel to AN or PV. Draw Q prime L perpendicular to QL. So this point is QL and this is Q prime L. So Q prime L is perpendicular to QL. So basically I have drawn this entire line and this entire line and then taken the intersection as L. Now draw QD perpendicular to PV. So this is PV. So from Q we draw a perpendicular to PV by extending PV. We have extended PV to D and then we have taken QD. So again, this line I have taken it fully and QD I have taken it fully and then the intersection is D. Now draw a cone with a conic around BB prime as the base and A the vertex. A is the vertex and that intersection of this plane with this plane is the conic, which is the base of this cone, and A is the vertex. Again, draw a cone with the conic around QQ prime as the base and P as the vertex. Okay, so we have these two cones. Now that you have seen this cone, let me remove it. As and when required, we will bring it back because it hides a lot of things behind it. Okay, so now draw PK perpendicular to QQ prime. Okay, so let's draw PK. So the construction part is over. Now let's start with the proof. Now triangle ABB prime, triangle PQQ prime is equal to triangle ABB prime. These two are equal in areas. This is based on proposition 3, which we have seen previously. And the reason is AN is equal to PB. Remember, let A and PB be the equal axis of the segments. So if they are equal, then these two areas are also equal. Means QD is equal to BN, again from proposition 3. Now, height of the cone PQQ prime is PK. Since cones are in the ratio compounded of the ratios of their bases and their heights. So we have two cones, remember? So those are in the ratio compounded of the ratios of their bases and their heights, which means cone ABB prime is to cone PQQ prime is equal to BB prime square is to QQ prime times Q prime L times AN is to PK. BB prime is equal to 2 times BN, because BN is, or N is the midpoint of BB prime. So BB prime equal to 2 times BN. 2 times BN is equal to 2 times QD, because QD is equal to BN. And 2 times QD is equal to Q prime L. And QQ prime is equal to 2 times QV, because again V is the midpoint of QQ prime. So cone ABB prime is to cone PQQ prime is equal to, remember here we had BB prime square is to QQ prime times Q prime L times AN is to PK. Now if we do the necessary substitutions, we will end up with equal to QD is to QV times AN is to PK. So BB prime square is to QQ prime times Q prime L is equal to QD is to QV. Now, again, cone ABB prime is to cone PQQ prime is equal to PK is to PV times AN is to PK. Because these ratios are equal, remember, the ratios are equal. Doesn't mean QD equal to PK, but the ratios are equal. So cone ABB prime is to cone PQQ prime is equal to AN is to PV. Now, how did we get this? Here, if you notice, PK is the antecedent, and here it is the consequent, and we are left with AN is to PV. We have reached this stage. Now, what's next? Cone ABB prime is equal to cone PQQ prime. Why? Because AN is equal to PV. Since AN is equal to PV, that means cone ABB prime is equal to cone PQQ prime. Remember, here we are talking of the cones. So the volume of these two cones are equal. But we know in proposition 22, we had seen the previous proposition that segment of the paraboloid ABB prime is equal to 1.5 times the cone ABB prime. And segment of the paraboloid PQQ prime is equal to 1.5 times the cone PQQ prime. Now, since these two cones are equal, that means their 1.5 times of each of them will be equal to each other. That means the segment of the paraboloids, segments of the paraboloid will also be equal. Finally, we can say segment of the paraboloid ABB prime is equal to segment of the paraboloid PQQ prime. So that was proposition number 23 of works of Archimedes, specifically from on conoids and spheroids. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now. Bye.